So exercise electrode potential and the transition metals. We did first 14 questions, so we'll start with question 15. This is an important exercise as almost half of your unit 5 based on this this topic. So 14 already recorded, so we'll start with question 15. Then this question is about the redox reaction. Vanadium exists in different oxidation states, which can be interconverted using suitable oxidizing and the reducing agents. Some relevant standard electrode potentials are shown. You can see for zinc, if an electrode potential is negative, it means the opposite reverse reaction is feasible. If the electrode potential is positive, it means the forward reaction is feasible. Because if positive electrode potential means forward reaction happen or it will gain electron. If a negative electrode potential means the tendency to lose electron is more. Higher the negative electrode potential, greater the tendency to lose electron. So we have to write overall equation for oxidation of vanadium 2 to vanadium 5. State symbols are not required. So vanadium 2 is vanadium 2 ions to vanadium 5. So which equation involve vanadium 2? So when we check which equation involve vanadium 2, and vanadium 2 to vanadium 5 we need. So if you see this equation, here we have vanadium 2 is there. And this equation so write overall half equation for oxidation of vanadium 2, like we have vanadium 2 and we want to convert into vanadium 5. VO2 with a charge of plus, each oxygen is -2, so 2 oxygen will be -4, so vanadium will be +5, so that the net charge is equals to +1. Now, whenever we want to write a redox equation, we balance oxygen. How we balance oxygen? We add water molecules. So one side we don't have oxygen, other side too. So here we should add 2 water molecules. So when 2 water molecules are added, the oxygen is balanced. Then to balance the proton, to balance the hydrogen, we add proton. 2 multiplied by 2, 4. So 4 hydrogen. So we need 4 protons. And to balance the charge, we add electrons. So what is the net charge? Here the net charge is +1 and +4. So the total net charge is +5. Here the net charge is +2. Water is neutral, so it is +2. Which side will add electron? The side where we have greater charge, that side will add electron. So we want to reduce the charge here because when we add 3 electrons, so when 3 electrons are added, +5 -3, so the net charge will be +2 on both sides. So this is a ionic half equation for conversion of vanadium 2 to vanadium 5. Select from the table reducing agent which can reduce vanadium 5 to vanadium 4 but not to vanadium 3. So we want vanadium 5 to 4 but not to 3. So first, what are the reducing agents here? Reducing agent itself, it is oxidized, and oxidation is a loss of electron. So what we want a vanadium 5 to turn into vanadium 4. How vanadium 5 will turn into vanadium 4? By gaining electron. So we will check a reagent which will lose electron. So the reagent which can lose electron, that and a vanadium 5 can gain electron, so it will turn into vanadium 4. So which equation first? We have like vanadium 5 to 4. So this equation we have, because if it is VO2 with a charge plus, so this is minus 4, this will be plus 5. So vanadium is plus 5. And this equation, we have VO2 with a charge, so each oxygen is minus 2, so vanadium should be, the total net charge is plus 2, so vanadium will be plus 4. So this is a conversion from plus 5 to plus 4. So we are looking for a reducing agent, because the first thing, the electrode potential should be positive. The electrode potential of a cell, it is redox, means reduction minus oxidation. And how we know which one reduction happened? The one which is having a higher voltage, reduction will happen for that. And the one which is having a lower voltage or a more negative voltage, then oxidation will happen. And reduction minus oxidation, if we get a positive result, it means that this is feasible. If we get a negative result, means it is not feasible. So we have different reagents are there. We want to compare this one with the other reagent so that we get a positive answer. So if I use iron here, so what will be the cell voltage? It will be reduction minus oxidation. Like if we use these two, if we use these two, reduction minus oxidation, so it will be 1 minus 0.77. So we get 0.23 volts. The one which is a higher voltage, reduction, and the opposite one, oxidation, will happen. So means this reaction is feasible. So iron 3, like this reaction is there when iron 2, and iron 2 will react with vanadium 5. Vanadium 5 will turn into vanadium 4, and iron 2 will turn into iron 3. And we don't want the 4 to convert into 5. Like in the question, they're saying vanadium, it will not convert vanadium 4 to, it will not convert vanadium from 4 to 3. So which equation involve vanadium 4? So this equation involve vanadium 4, because VO with a charge of plus 2, so each oxygen is minus 2, vanadium is plus 4. So this is a conversion of vanadium 4 to vanadium 3. If we use the same reagent, because in the question we have to deduce the reducing agent, which will reduce iron vanadium 5 to 3, 5 to 4, but not 4 to 3. So when we are using for first one, it happened. Now in this one, what will happen? The one which is a higher electrode potential, reduction will happen. So for this change, reduction will happen, and this will oxidation happen. So here iron 3 will convert into iron 2, but vanadium 3 will convert into vanadium 4. So means this reagent can convert 5 to 4, but not 4 to 3. Is it clear? So if we use iron and we compare it reaction with vanadium, because this is from 5 to 4. So when we compare 5 to 4, because this is a higher electrode potential, so reduction happen here, this will be oxidation. The one which is a higher electrode potential, always reduction happen, and the opposite one, oxidation happens. So Means iron 2 will convert into iron 3 and vanadium 5 will convert into vanadium 4. But when we check the reaction here with this one, like this is a conversion of vanadium 4 to vanadium 3. But when we check, this is having a higher electrode potential. So when they are reacting, this will reduction happen and this will oxidation happen. So the iron 3 or iron, so opposite will happen. If reduction happen, iron 3 will convert into iron 2 and the vanadium, its oxidation happens. So vanadium 3 will convert into vanadium 4. So how we'll write this answer? First thing, we'll mention the reducing agent will use iron 2. And the first part, when it is reacting with vanadium 5 compound, the electrode potential of a cell is positive. So reduction happen for vanadium and oxidation happen for iron 2. But when we are reacting for this compound with vanadium 4, so the electrode potential is negative for the cell, so it means the reaction is not feasible. Reverse is possible, but the forward is not possible. Is it clear, this one? Second part? Okay. Then we have to write the balance equation for disproportionation of vanadium 3 to vanadium 2 and vanadium 4, because like here vanadium 3 is converted into vanadium 2 and vanadium 3 is converted into vanadium 4, and explain whether this reaction is feasible under standard condition. So we have to take the two equations in which this conversion is there from. So we have the table is given. First, we have to write a balance equation, because we want vanadium plus 3 to turn into vanadium plus 2 and vanadium uh, plus 4. These are this, because like vanadium as an ion can exist as plus 2 or plus 3, but it is a molecule in a state of a plus 4. It does not exist as a free ion. It is existing as a molecular ion with oxygen. So first, again, we have to write a balance equation. So how to write a balance equation? If you want to balance oxygen, we add water. So we add one water molecule here. If we want to balance hydrogen, we add protons. So two hydrogen, so we add two protons. And to balance the charge, we add electron. Here we have plus 2. Here we have plus 2, and plus, so total is plus 6 because this 2 is, so plus 6 is there, and here we have plus 3. So means how many electrons should be there? There should be 3 electrons. Now when we check the equations which are given for conversion, electrode potentials are given, because we have to use this table. So one is vanadium 3 to 2. Another one is vanadium 3 to 4. So according to this, what will be the voltage of a cell? Voltage of a cell is reduction minus oxidation. Like it is redox. So what actually happened? Like in this case, the vanadium 3, because when an electrode potential is positive, this electrode potential is positive, so means this forward reaction is feasible. So what actually happened? Vanadium 4 will convert into vanadium 3, and This is negative, so reverse is possible. So vanadium 2 will convert into vanadium 3. But we want the both to be, so this will be like 0.34 minus and then negative 0.26. So according to this, like vanadium, when a positive voltage is there, so it means the plus 4 should convert into plus 3, and here plus 2 should convert into plus 3. But what we want plus 3 to convert into plus 2, and we want plus 3 to convert into plus 4. Like the same element, we want it to be oxidized and reduced. So if we use a reduction minus oxidation, so 4 will convert into 3 and 2 will convert into 3. So both of them will convert into 3. So means this is not feasible. Like 3 is not converting into 2 or 3 is not converting into 4. What actually happened when we work out the electrode potential, 4 will convert to 3 and 2 will convert into 3 if we mix them together. Or there is also another way you can work out, like you just compare the as we want to work out the cell voltage. So according to cell voltage, what is the formula here? Plus 3 is converting into plus 2. So what is the voltage? That is minus 0.26. So we write minus 0.26. And here plus 3 is converting into plus 4. So it should be like, if a plus 4 convert into plus 3, the voltage is positive. But if a plus 3 convert into plus 4, the voltage should be negative. So we write as negative 0.34. So when we write both of them as negative, we get a negative answer. It means the reaction is not feasible. So you can work out the idea of the electrode potential. If you get a positive answer, then it is feasible. If you get a negative answer, it means the reaction is not feasible. So this reaction is not feasible. In part B, potassium iodide solution was added to 25 cm cube. The iodine produced were titrated with sodium thiosulfate. All the iodine required 24.20 cm cube of sodium thiosulfate. Calculate the concentration of solution of bromine. So first, we have the volume and concentration. We get the moles of thiosulfate. From moles of thiosulfate, we'll get the moles of iodine. And from moles of iodine, we'll get the moles of bromine. And after getting a moles of bromine, we'll divide it by the volume, so we get the concentration. So first, moles equal concentration into volume, moles of thiosulfate. Concentration is 24.2 divided by 1000. This will give us the moles of thiosulfate 0.0024. Then we use the ratio between the iodine and thiosulfate. It's a fix, that is 2:1. So if we have moles 0.0024, then this will be X cross multiply. We get the moles of iodine, which is 0.00121. And then finding the moles of bromine, it is a ratio 1:1, so we get the same moles. But to get the concentration, it will be moles divided by volume. So moles of bromine 0.00121, and the volume of the bromine is 25. We have to convert into decimeter cube divided by 1000. So 0.0484 moles per decimeter cube. That is a concentration of a bromine solution. In second part, in another experiment, 100 cm cube of a same solution of a bromine was titrated with 0.001 mole thiosulfate. Excess of a potassium iodide was then added to unreacted bromine. The iodine produced required 16.8 cm cube of 0.1 mole per dm cube thiosulfate. Deduce the mole ratio of thiosulfate to bromine, hence write the balance equation for a reaction between the thiosulfate and the bromine. State symbols are not required. So we have a bromine solution. First, a bromine solution directly mixed with thiosulfate, and what is left is reacted. Then solution of a bromine is directly added to thiosulfate. Excess of iodide, which is more than enough, added to unreacted bromine, and then which produce iodine molecule. An iodine molecule reacted with thiosulfate with this concentration. So we want to work out the balance equation for this. So initially we have the concentration. First we'll find how many moles of bromine are there, the total number of the moles. We have, so this is the total volume. We want to work out how many moles of bromine are there. So moles of bromine, that is concentration into volume. The concentration of a bromine, which we calculated in the previous part, 0.0484, and the volume of the bromine is 100 cm cube divided by 1000. This will give us a total moles of a bromine, which is 0.00484. These are the moles of bromine. Then moles of thiosulfate, which are reacted with iodine. The moles of thiosulfate, which reacted with iodine. This part, iodine, which is produced, reacted with. So we can use moles equal concentration into volume. So concentration is 0.1 and the volume is 16.8 divided by 1000. This will give us the moles of iodine, moles of thiosulfate, which are used, reacted with iodine, 0.00168 mole. Then to work out the moles of iodine, we'll take a ratio between thiosulfate and iodine. So this is always a fix. Thiosulfate to iodine ratio 2:1. This is X and this was 0.00168. So how many moles of iodine are there? That will be 0.00084 mole. So we got the moles of iodine. Now, like how many moles of a bromine are in excess? Because these are the moles of iodine and moles of bromine will also be same. Why it will be same? Because the ratio between bromine and iodine is 1:1. So same number of moles of bromine will be there. These are the unreacted moles of bromine and these are the total moles of bromine. So how many moles of the bromine are reacted? So reacted the total moles which were 0.00484 minus the moles which are unreacted 0.00084. So we get 0.004 moles. These are the moles which are reacted. Now we want a ratio between the moles of a bromine and thiosulfate to bromine according to. So S2O3 and bromine, the moles of a thiosulfate were. So this give us the moles of bromine, the last part. Now, in the beginning, this many moles were used. So 0.000, and this was 0.004. So ratio is 1:4. This gives us a mole ratio. Is it clear? And the last part, we have to write a balance equation between them. Now, how to write a balance equation? First, we identify the moles, the mole ratio. That is 1:4. So for thiosulfate, and for bromine. These are the moles of thiosulfate which are given in the beginning, which are reacted with added to bromine. 0.00, these are the moles of thiosulfate which reacted with unreacted. Look what we did. We have a bromine solution. We add thiosulfate. Bromine is in excess. Excess of a potassium iodide was added to unreacted bromine. So this thiosulfate, all moles reacted. Then bromine unreacted moles are there. Those unreacted moles react with iodine, iodine, form iodine. And that iodine which is formed is reacted with thiosulfate. So thiosulfate is used twice. One is to react with bromine, and the second one is to react with the moles of iodine produced by reacting with excess of a bromidine or bromine. Clear? The next we have to write a balance equation. We worked out the ratio is 1:2. So S2O3 reacted with bromine. The ratio between them is 1:4. Now we want to balance the equation again. How to balance a redox equation? If you want sulfate reacted with bromine, first you should know what products are formed. So it form a sulfate, SO4 ion is there, and it also produce bromine molecule turned into bromide ion. Then the next one, after knowing the products, we have to complete this. So if you want to first balance these other element like S2 is there, we should have 2, so this should be 2 here. And bromine 8, so 4 multiplied by 2, 8, so it should be 8 here. Then to balance hydrogen, to balance oxygen, we add water, 4 multiplied by 2, 8, plus here we have 3, so how many we left? 5, so we should add 5 water molecules. And to balance hydrogen, we add protons, so 10 protons should be added, 5 multiplied by 2. And to balance the charge, you can add electron here, neutral. Thiosulfate is -2 here. And here -2 and -8, like -8 plus 10. So this will be +2. And this will be 2 multiplied by 2 makes -4, -8, so -12. And -12 plus 10, so it will make -2. So both are in -2. So we don't have to add electrons at all. So this equation is balanced. This is a balance equation. So electrode potential and the transition element is the one of the most important topic in unit 5. You have to be very good in this